All right, you guys, so we are going to go ahead and graph log functions today. So yesterday we did our exponential functions, and they looked a lot like this right here, this graph on the right. So I've already filled in a little bit. They're just the basic form of a log function, right? Log with a base b of x. And then I'm now showing just the basic graphs that you might compare, right? This is the common log, so it's got a base of 10. And then this is the function 10 to the x, an exponential. We saw yesterday that exponential functions have a horizontal asymptote, right? So this one would be y equals 0. And I told you yesterday, because logs are inverses, you're kind of inverting each piece, right? So instead of having a horizontal asymptote, now I'm going to have a vertical asymptote. So this would be instead of y equals 0, at x equals 0. And then our function, if you can kind of see, is just inverted, right? It looks like the opposite thing. If I were to spin this around, that would look similar to a log function, but flipped, right? So as we're going down here, I'm going to do an example or two and just kind of remind you of the methods we used and how we might transfer this over to logs. And then I just want you to try the rest, do your delta math, and, have a wonderful weekend, and we'll pick it back up on Monday. So plans for right now. To graph any kind of log function, they do give you advice here that you can use the inverse exponential function. So in other words, like turn log base 3 of x into 3 to the x, and then take those points and invert them. Or you can kind of think in the same way we thought yesterday, right? To get our points yesterday, we always started here. We said, okay, either 0, 1 are our points, or if we have a fraction, I'd pick 0 and -1, for example, right? But instead of doing that here, instead of making my x values 0 and 1, I'm going to make my y values 0 and 1. The reason is because when you're plugging things into logs here, we cannot plug in 0, right? That's the whole point of us not being able to have any values there. We have a vertical asymptote at 0 because this cannot happen, right? So instead of plugging things in, I am going to actually guess my y values and then solve. So I'm going to show you why we do that. So if I were to set my y equal to 0 in this case, this is your snail trick, right? Now I can just solve, right, and figure out and go backwards to figure out what would I plug in to get that, right? Because going the other way, you can guess that as well and figure out what makes sense. Either way is fine, but using the same trick as yesterday, I just think inverse. Instead of my x's, I'm putting my y's, right? So now 3 to the 0 gives me 1. So I got my first point, 1 comma 0. And then if I were to redo this, right, maybe I'll move down. If I were to do the same thing, but replace these with 1, right, 3 to the 1 gives me 3 as my second x value. All right, you can also think 1, 0 is generally going to be a point that we see quite often because anything to the 0 power gives you 1, with the exception of transformations. And then also, this is going to be a common thing you see as well, right? If you plug in whatever the base is, log 3 of 3 is 1. Log 5 of 5 is 1, right? So no matter how you twist it, you can always use your calculator. You will end up with points, similar or nearby what I have. So I'm going to plot down my points, 1, 0, and then 3, 1. Connect my dots here. So instead of having a horizontal asymptote, you got to know here, I have a vertical asymptote, right? And because there's no transformations happening here, our asymptote doesn't move. So it's going to be at x equals 0, right? For my x-intercept, now we're not filling in y-intercepts because in this case, we're not going to have any, right? There is a chance if there's a transformation that we do have one. In this case, we don't. Remember what I said yesterday, that all exponentials have a domain that's all real numbers. Well, here the domain is not all real numbers. So we're actually inverting that as well. Now my range is all real numbers because I can go up and down and hit all values. But my domain this time is going to change. It's going to be 0 to infinity. Now, for the rest of these pieces, you got to guess, okay, is my graph increasing or decreasing? Well, it appears my graph is increasing on the whole interval, but it's not increasing from negative to positive infinity because nothing even exists over here, right? I'm really increasing on my domain. So you're always going to copy down that domain when you do problems like this, but it just so happens that the domain is different for this problem, right? And then we're decreasing nowhere. Now I'm going to do my end behavior. Maybe we'll start on the left and then do our right side. On the left side, this is unique because do I ever approach negative infinity? No, my left side is just right here, right? That's as far as I'm going to go. So pretty much on my left side, you're going to think, well, what's going to happen when I go to the left? I'm just going to approach 0. There's no way that I can get any farther than that, right? As I approach 0, my graph is going down. So I'd be down at negative infinity. And then on the right side, my x is going positive and my y is also going positive, right? So that is one of the simpler examples. No transformations, kind of like how we warmed up yesterday. That's how I get my points, right? Instead of setting my x's 0 and 1 or 0 and negative 1, I set equal. So set my y's to 0 and 1 or 0 and negative 1. That is the general idea. Now, I want to scroll down a little bit. You can try some of these, maybe pause the video and try a couple as well. But number 4 is another good one for us to take a look at, because you should notice there's something different here, right? I've got a transformation. Now, you should know this is moving my graph up 1. So is that going to affect a vertical asymptote? No, nothing's going to affect that, right? But something that's on the inside, so something like this in number 5, that is going to affect my asymptote. This is going to make my asymptote 2, right? So I wanted to kind of mention that when you're going through, if you get really stuck, those transformations do matter in this case for you to understand what's going to move something and what might not, right? Your calculator can't just immediately tell you what the asymptote is. You kind of got to know where to start to at least brainstorm what it might be. The calculator might help, right? So to find my points, this is what I might do. I might do the same thing and say, okay, I'm just going to stick to parentheses, get 2 points, figure out what's going to make this 0 and what's going to make this 1. All right, I'm going to move these down and then figure out, just set up an equation, right? Because now I'm figuring out what x is, but I'm setting equal to 0, right? So, well, what happens? Well, if this was a normal equation, we'd subtract 1. Now we've got a log equation that we can do our snail trick on. So then I've got 1/3 to the negative 1 power, gives me my input, so that's going to have me at a first point, 3, 0. So if you see how I got that, I'm just kind of flipping. If this part confuses you, you do have the calculator. You can also just brainstorm and guess stuff that works there. Many options here that you could use, right? And then to get 1, I'm going to zoom down a little bit. To get 1, if we did this, 1/3 x plus 1 equals 1. When you subtract 1 from both sides, now you have equal to 0. And remember, anything to the 0 power gives me 1. So I still have 2 nice points that I can put down on my graph that help me. And another log graph that you can see, right? It looks a little bit different than maybe some of the ones that we just saw, that we just graphed together, right? And some of the ones that you'll see on this page, you know, some of them look very different. This is a decay function, right? Different than what we saw that was a growth function, increasing on the whole interval. So unique things you'll see, stick to the 2 points. And then in this case, a lot of our pieces really end up staying the same, right? My x-intercept now changed. That one is 3, 0. Still have an asymptote at 0. Now I'm not increasing. I happen to be decreasing, and I almost screwed that up, but we're decreasing still on 0 to infinity, right? And then these end behaviors, as I'm going to the left side, I'm still going towards 0, but now I'm going up when I go to the left side, right? As I go this way, I'm going up, and then as I go to positive infinity, I'm going to hit negative infinity. The order of these does not necessarily matter, right? If you put this one second, if you flipped them, that would be totally fine, but this would be our number 4, right? That's really kind of the idea. So the only other thing, again, that you will see, and I want you to just try number 5 and kind of brainstorm what might happen in this case. I did talk earlier about how this is going to change your asymptote, right? Instead of it just being at 0, like we've seen in all these problems, the x transformation, moving right and left, that is going to change a vertical line, right? If I move that right and left, that's going to change it. If I move it up and down, nothing really happens, right? It's a terrible line, but that's okay. So that's the idea here, you guys. This would start out, I'd start out by straight up putting your asymptote down and then see what kind of points you can come up with, all right? So I'll tell you right now, I end up with points here and here. All right, so maybe take a look at that answer key. Check all your answers for these pieces, the end behavior, but notice what might change those asymptotes as you go through and as you try these. There is a homework assignment, should be posted already. The answer key's out there, but use this video if you do get stuck on kind of the brainstorming and how to find these pieces. So good luck. Bring in questions Monday if you got any. All right, have a good one.